Next, I want to look at proving equality of sets. So how can we prove that two sets are equal? If we have the rosters, like the roster notation, you can do it that way too. So if you're able to actually find these values like we did in like the first example, then you could actually compute each one of them and then show that they're equal that way. So that would be for a specific example. But in some cases, we want to prove overall that operations are the same. So here, we're trying to show that if you take the intersection of A and B and then its complement, that it's always equal to A complement union B complement, no matter what A and B are. They could be any elements in the world. This is always going to work for all sets. So in that case, we can't use just the roster notation because I don't have specific elements. I'm talking generally here. So I want to prove it in a general set. So what I can do is use the Venn diagram to prove this. So if both sets are represented by the same regions in the Venn diagram, then this proves that they are equal. So I have my general Venn diagram here with sets A, B. I'm assuming there's some overlap. And then I have parts 1, 2, 3, and then 4, just all labeled to make it easier to work with. So I'm going to start on the left side. A intersect B complement. And I'm just going to go through piece by piece. And you can see your book uses a table there. So if you want to do that too, you can go ahead and use a table. I'm just going to kind of list my steps instead, but they both work well. So I do say I have parentheses here. So the first thing I need to figure out would be what is A intersect. So my first step is A intersect B. So if I look at my Venn diagram, where is A intersecting B? Well, it's right here in the middle, right? So this middle piece here is A intersect B. It always is. So my first piece is the region 2. Now I want to take the complement of that. So now I want to take that intersection and take its complement. So I want everything that is not A intersect B. Well, think about all the other regions. I have region 1, 3, and 5, right? Those are all the regions that are not region 2, which is A intersect B. So my answer here would be regions 1, 3, and 4. Sorry, this is 4. I think I may have said 5. That's 4. All right, so that's the first part. So our answer ends with these 3 regions. Now I'm going to do the other half, this side. So the first thing I'm going to do, I don't have parentheses here, but I am going to find my complements first. It's much easier to do it that way. So I'm going to figure out what A complement is first. So A complement means not A. So A is right here, right? This is my A. So the 2 regions that are not in A are regions 3 and 4. Then I'm going to figure out not B. Well, I'll use a different color. B is here. So the 2 regions that are not part of B are 1 and 4. And now I want the union of them. So I want to combine those together. So I see I have region 1, I have region 3, and I have region 4. I don't have region 2, right? I don't need to repeat the 4th region either. So region 2 is not included. I have 1, 3, and 4. So I have what each of these look like in the Venn diagram, and notice that they are the same. 1, 3, 4, 1, 3, 4. These are the same, and so they are. So we've proved that this sort of formula or this operation works no matter what sets A and B are. Like I said before, if you have a specific set A and B, then you could find the roster notation and show it that way. But this method of using the Venn diagram proves it in general. So you're not proving it for a specific example, you're proving it for all examples with A and B. So these can be really helpful, particularly if you're going up in mathematics and you're doing a lot of work with sets so that you don't have to continuously prove this every single time. You can now use this. And we actually have, this is one of them, but we actually have 2 laws called Morgan's law. This is the first one that shows that the intersection or the complement of the intersection is equal to the union of the 2 complements. And you can do something similar. So if you want to try it on your own, you can prove the other way. So the complement of the union is equal to the intersection of the two complements. So it's the same idea, but notice that the notation flips. So here you're going from intersection to union and from union to intersection. So both of these laws can be proven. We prove the first one, and you can prove the second one doing the same thing. So if you want to try that at home, I definitely encourage you to do so. All right, let's do one more of these. And now I'm looking at 3 different sets here. So again, I'm just going to start with a general picture. Let's do it in blue. And we typically assume that there's probably some overlap between the 3 sets. I don't really know, but I'm going to just draw my Venn diagram like that and just make that assumption. So here I have A, here I have B, and again, your circles don't have to be to scale. Here I have C. And I'm just going to label each part. I'm going to label them consistently with your textbook so you can follow along there. And why this keeps on focusing. All right, so this here is part 1, region 1. This is region 2, region 4, 5, 6, and 7, and then outside. Okay, and again, we're going to do the same idea. So we're going to prove that these are actually equal using the Venn diagram. So it proves it for all sets, and we're just going to use our different regions to help us show that the 2 regions are the same on each side. So on the left, I have A union B intersect C. So again, I'm starting with the left side first, just going one at a time. I have parentheses. So my first thing I'm going to do is look at just B intersect C. So where does B and C overlap? So here's B, here's C. And notice that right in here, these 2 little regions are where B and C overlap each other, right? So 5 and 6 are included both in B and in C. And then now that I have that, I'm going to combine that or make it a union with A. So all my regions for A are 1, 2, 4, and 5, right? That's all A right here. And I already have 5, but I have to combine this with B intersect C, so I'm going to add in 6. Now I'm going to do the other side. So this one right here. I'm just going to write it down over here. So I'm looking at A union B intersect A union C. And again, I got to do this parentheses first. So I'm going to do A union B. So I'm looking for A and B together. So all the regions that contain A and B. So I have, let's see, 1, 2, 4, and 5 for A. And then B contains, let's see, 2 and 5 already, but then also 3 and 6. So I'm just writing those down here. Let's see if I can zoom out a little bit. And then I'm going to do A union C. All right, so where do A and C overlap? So the regions for A are 1, 2, 4, and 5. 4, 5. And then for C, it's this group right here. So I have 4 and 5, which I already have. I have 6 and I have 7. And now I'm looking for the intersection. So remember, the intersection is what they have in common. So they both have 1 in common, both have 2 in common, both have 4 in common. Let's see, they both have 5 in common. They both have 6 in common. So 1, 2, 4, 5, and 6. And notice this matches here. 1, 2, it's a little messy. This was 4, 5, 6. So these are the same regions. So we have equality.